Welcome to Week 5's first lesson on the subsurface of Nebraska. So this is mini lecture 9 in our series. Today we're going to be talking about how exactly we look below the surface and a little bit about what's below our feet actually. So for this mini lecture, I'm just going to review some of the ways that you'll actually be looking at below the surface and then introduce the rocks that you might see way down below our feet. So today we'll first talk about trenching, then coring, then geophysical probes, geophysical remote sensing, and finally a few other methods. Now trenching or trenches is literally just digging into the dirt or anything that's capable of being removed below our feet near the Earth's surface. So this is typically looking at only a few feet to a few meters long. And so here in this image, what we're looking at is a trench that actually has exposed a recently faulted surface. So there is a line here in the center if you follow my cursor, and that line is where two blocks of material have faulted or broken apart. So we can see structural features by digging just below our feet. Coring is probably the most used method of looking below our feet. The deepest drill hole ever done is 12 kilometers deep, which is about 7.5 miles, just over that. There are various different coring methods that have been developed. Some for very short cores, which is pictured in the bottom here. This is actually me and my colleague Chavi doing field work collecting a sediment core from a lake. So what I'm holding there is some lake mud that we've taken with a core. But also there have been methods that are much more expensive than that little tiny core we're using in the bottom photo. And in the top photo, that's just showing one of these more expensive, more elaborate drilling projects. So this rig up here would be drilling into the bedrock, which is the hard material. So it can be used for bedrock, unconsolidated sediment, and ice core records, as we'll see. And there are actually hundreds of thousands of holes drilled just in Nebraska. Typically, these holes are drilled for groundwater exploration or hydrocarbon exploration to find oil and natural gas, though some of these are explicitly used for research. So some things that use cores to study geology are paleolimnology, which is what I do. I'm a paleolimnologist. So we use lake sediment cores to reconstruct lake histories. So shameless plug, but I'm teaching a class in the fall in person on paleolimnology. You just need 12 credit hours of an intro science to be eligible to take it. So if you are interested in that, let me know. But we use lake sediment, which is unconsolidated sediment, to study the past. Ice cores can also be used for these studies. So basically what you do is you drill using hot water and obtain a ice core from continental ice sheets like in Antarctica or Greenland, but you can also obtain them from mountain glaciers. Paleoceanography is similar to paleolimnology, but instead you'd be drilling or coring ocean sediments to reconstruct ocean histories. And that can be used in turn to reconstruct past climate change. It can be used to reconstruct ocean circulation patterns. So there's lots of different things you can do with these cores. And then finally, on the more practical side, in the recent past, is using these bedrock cores to determine rock layers that are rich in hydrocarbons. Many of these cores that were taken for this purpose have also been used for other scientific studies, including geochemistry of the rocks, the structure of the rocks, as well as mineralogy and paleontology. So here are some images of these cores. On the left is a core our research group took in Ecuador. So those gray layers are actually tephra, and if you remember from last week, or the week before last week actually, tephra is volcanic ash. So what you're seeing here is a volcanic ash layer, possibly similar to what you would see at ashfall. On the right top is an image of one of those bedrock drill cores. You can see the laminations. Those would be changes in minerals. And then the bottom, this is an ice core in the bottom right. So just an example of what these different cores would look like. Now, when you're looking at bedrock cores, often geologists are trying to correlate them or figure out where that rock layer extends to laterally. So you can correlate these cores by connecting rock layers with similar characteristics, such as rock type or fossils within those rocks as well. So in this image to the right, I've correlated these layers. The blue layers are limestone, the gray are shale, and the yellow are sandstone. So at the top, you can see that there are two limestone layers in both of those cores. So we can assume that there's a layer of limestone that extends laterally in that direction. Same with the shale below that and the sandstone below that. Now we have a curious case in the middle here, where on the left-hand core, we've got shale, limestone, followed by shale, whereas in the right core, we just have shale, no limestone. So what that implies is that that environment that was depositing this middle limestone did not extend as far to the right in the past. So we had shallower water on the left-hand core and deeper water on the right-hand core. So at some point this layer pinches out, and that's what that triangle is representing. So we can actually use these to reconstruct changes in sea level. And you'll see this multiple times in Geology of Nebraska. So keep that in mind as we go forward. Geophysical probes are also used to look below the surface. So these refer to basically kind of probes that are dipped down into the empty drill core. So they're used after the material is obtained, and then the empty drill has the probe dipped down into it. So here we can use electrical resistivity, which is the resistance to electric current. So that's basically used to determine whether a layer that has pores or water in it is briny or salty versus fresh. So that can tell how much ion content is in the water. Now, density logs are another probe method that's used. So they basically bombard material with radioactive isotopes and then measure the gamma waves that are produced from that bombardment. So that's a measure of porosity, and we'll see what porosity is in a moment. And then gamma ray log is next, and that measures the natural radioactivity of a material, so the radioactivity that the material itself is emitting. And that's a good measure of sandstone versus shale. Shale emits a lot of radioactive material. And then the last one is spontaneous potential log, which is used to determine impermeable layers, or layers that can't have material flowing through it. So that's another way to tell how there's a difference between sandstone and shale. So I've mentioned porosity and permeability in the last slide, so I just wanted to touch on what that is. So important factors in groundwater and hydrocarbon exploration, which are often what we're drilling for cores, are porosity and permeability. And porosity is just the amount of pore space available in a material. So that's shown in the bottom left image. The leftmost image in the left corner is a material that has a high porosity. All of the blue space is open space, and the black dots indicate mineral grains. Now on the right, when there's two mineral grains of different sizes, we can see that the blue space is less. So with less blue space, there's lower porosity. If there's low porosity, you can't have a lot of groundwater in there. You can't have a lot of hydrocarbons in there. So when you're looking for those things, you want a material that is very porous. You also are looking for a material that's very permeable. So permeability is the ability of a fluid to flow through a material. So on the right-hand side, this image is showing both porosity and permeability. So starting on the left-hand side of that diagram, there's no pore spaces. The mineral grains are so close together, there's absolutely no space between them, so low porosity. And because of that, those pores aren't connected, so nothing can flow through it. So it's non-permeable or impermeable. As we move to the right in the center, we start to have some pore space indicated by the blue color. So it's porous, but those pores are not connected. They're cut off from each other. So that means it's still impermeable. Now on the farthest right, this is an area where pore space, or it has a high porosity, and those pores are connected. So because those pores are connected, we have a high permeability. So just kind of showing the range of porosity and permeability that you can have in different materials. Next, we're moving on to geophysical remote sensing, and this is what we talk directly about in the lesson today. So this really shows us what is the deepest below our feet, the very bedrock, or the basement bedrock. So we call it the basement because it's the material that is furthest down before we hit asthenosphere. And so here, what we're looking at are two geophysical remote sensing methods. On the left, we're looking at a map of magnetic anomalies. So there are very, very, very fine differences in magnetism within different rocks. And so there are remote sensing methods that can detect those magnetic signatures in the rocks and produce maps. So each color here is assigned to a certain magnetic measurement. And so the rocks that are pink in color have a really high magnetism, whereas the rocks with bluish colors have a low magnetism. So that can tell us what type of rock might be there. And then on the right is another type of geophysical remote sensing, and so this one's a gravity anomaly map. And in the same way as the magnetic anomalies, certain rocks are more dense than others, so they have very, very fine differences in gravity, which may seem crazy, but very, very, very minute differences, and we can sense that remotely. So we can produce similar maps to what you might see on the left-hand side. In this instance, we have our change in gravity here on the right-hand side, and those colors have been assigned. But you can really see some features here, and in the lesson, you're going to be paying attention to the patterns that you're seeing in these features. There are some other methods of looking below our feet that we're not going to really discuss or focus on today. There's seismic reflection, and this is how we can kind of detect structures in rock layers. So in this instance, you take a seismometer and you shoot beams into the seafloor, and it reflects back at you. And where it reflects back at you allows you to produce this map that's shown in the bottom. So we're looking at the reflection of these seismic waves. There's another method called seismic refraction, which works in a similar way, except for instead of looking at when it reflects back at you, you're looking at where it refracts or where it changes direction. So here you can see the lines are slightly different. We're not getting that reflection. We're getting a refraction where it changes direction when it hits a new layer of material, and then it's sent back up to the surface. Other methods for a little bit closer to our feet, maybe like 10 feet, you can use ground penetrating radar. And so this is shown a map on the right. Using ground penetrating radar, you can locate buried concrete rebar, certain metallic targets, so you can kind of reconstruct what's immediately below our feet without actually digging into the ground or drilling. So finally, before we finish today's mini lecture, I just want to discuss the rocks that are in the basement of Nebraska, or the rocks deepest below the surface here. So we're going to be looking a little bit at igneous and metamorphic rocks today. Again, we're not going to go in too great of detail about these ones because Nebraska barely has any, but deep below in the basement, igneous rocks are rocks that form as magma or lava cools. So we do have some igneous rocks in the basement of Nebraska, and that's pictured on the left. This pink, black, and white speckled, these are crystal grains, and this is a granite. And granite is an important type of rock in the basement of Nebraska. And then metamorphic rocks are also down there, and that's material that's previously existing, and it's been changed by high heat and or high pressure. So on the right, in the bottom here, this is a gneiss, Gneiss, and these bands are caused as mineral grains align from induced pressure. So some sort of mountain building event could have caused this. But gneisses are also found deep below our feet. So you'll take a look at some of these igneous and metamorphic rocks today. So to summarize, we can observe what's in the subsurface, and we do it through multiple methods. Cores are one of the main methods of doing this, but you can also use different geophysical techniques. And there are igneous and metamorphic rocks down there, so go ahead and finish reading through today's lesson and answer all of the associated questions. And if you have any questions for me regarding this material or anything else in class, feel free to get in contact.